Present the conference. The material of conference was organized by the engineer Jesus Velasquez Bermudez, Ph.D. Fundamentals of Optimization and Economics. Alfred North Whitehead was an English mathematician, physicist and philosopher, recognized as the defining figure of the philosophical school known as the philosophy of process, which today has found application in a wide variety of disciplines, including mathematics, ecology, theology, education, physics, biology, economics and psychology. In his early years, Whitehead wrote primarily about mathematics, logic, and physics. His most notable work is the 3 volumes of Principia Mathematica, 1910-13, which he co-authored with Bertrand Russell. Principia Mathematica is considered one of the most important works on mathematical logic of the 20th century and reached 23rd place on a list of the 100 best English-language nonfiction books of the 20th century. In the early 20th century, Whitehead began to focus more on the philosophy of science and eventually on metaphysics. He developed a metaphysical system that emerged radically from Western philosophy. Whitehead argued that reality consisted of processes, rather than material objects, and that processes are best defined by their relationships to other processes, thus refuting the theory that reality is fundamentally constructed of fragments of matter that exist independently of each other. Whitehead's philosophy holds that it is necessary to see the world as a network of interrelated processes of which we are integral parts, so that all our decisions and actions have consequences for the world around us. Optimization fundamentals. Lagrange theory, duality theory, KKT. Isaac Newton. Unconstrained optimization. Sir Isaac Newton was an English mathematician, physicist, astronomer, theologian, and author, described in his time as a natural philosopher, widely recognized as one of the greatest mathematicians, physicists, and most influential scientists of all time. He was a key figure in the philosophical revolution known as the Enlightenment. His book Mathematical Principles of Natural Philosophy, published in 1687, established classical mechanics. Newton also made seminal contributions to optics, and shares credit with German mathematician Gottfried Wilhelm Leibniz for developing infinitesimal calculus. Joseph Louis Lagrange, constrained optimization. Joseph Louis Lagrange was an Italian mathematician and astronomer, later naturalized French. He made significant contributions to the fields of analysis, number theory, and both classical and celestial mechanics. In mathematical optimization, the Lagrange multipliers is a strategy for finding the local maxima and minima of a function subject to equality constraints. The basic idea is to convert a constrained problem into a form such that the derivative test of an unconstrained problem can still be applied. The relationship between the gradient of the function and gradients of the constraints rather naturally leads to a reformulation of the original problem, known as the Lagrangian function. From now on, it will be considered a minimization problem. The definitions are similar for the case of maximization. The image presents the problem that Lagrange solved, which has n variables and m equality constraints. The implicit function theorem, IFT, is a fundamental result in multivariable calculus that provides sufficient conditions for a relation, typically a system of nonlinear equations, to define some variables as functions of others. Using IFT, Lagrange replaces the original problem with a system of equations of equality, introducing Lagrange multipliers, each associated with a constraint. The original problem will be known as the primal problem, and the one that includes the multipliers as dual. Lagrange multipliers are auxiliary variables that form the Lagrangian, whose gradients are equalized to 0, and solve the original variables and the Lagrange multipliers, establishing the points where the contours of the objective function are tangent to the constraint curve. The Lagrange multiplier defines a function that changes when its inputs are bound by specific conditions, finding optimal solutions under those constraints, which is crucial in fields such as economics, engineering, and physics. Therefore, he defines the derivative of the objective function as a function of the coefficient of the associated constraint. A Lagrange saddle point is a key concept in constrained optimization, where the Lagrangian function, formed by the objective function and the constraints, has a point that is minimum in one direction, along the original variables, and is a maximum in another, along the multipliers, which means optimal solutions for the primal problem of minimization and for the dual problem of maximization, fundamental concepts for convex optimization and duality theory. Duality theory. John von Neumann, duality theory. John von Neumann was a Hungarian-American mathematician, physicist, computer scientist, and engineer. Von Neumann was considered the mathematician with the greatest coverage of the subject in his time and was said to be the last representative of the great mathematicians who were equally comfortable in pure and applied mathematics. According to George Dantzig, the duality theorem for linear optimization was conjectured by John von Neumann immediately after Dantzig presented the problems of linear optimization. Von Neumann observes that he uses information from his game theory and assumes that a zero-sum matrix game for two people is equivalent to a linear optimization problem. Von Neumann made major contributions to many fields, including mathematics, foundations of mathematics, functional analysis, ergodic theory, group theory, representation theory, operator algebras, geometry, topology, and numerical analysis, physics, quantum mechanics, hydrodynamics, and quantum statistical mechanics, economics, game theory, computing, von Neumann architecture, linear programming, self-replicating machines, stochastic computing, and statistics. George Bernard Dantzig, simplex method. George Bernard Dantzig was an American mathematical scientist who made contributions to industrial engineering, operations research, computer science, economics, and statistics. Dantzig is known for his development of the simplex algorithm for solving linear programming problems, and for his other work with linear programming. In statistics, Dantzig solved two open problems in statistical theory, which he had mistaken for homework after arriving late to a lecture by Jerzy Neyman. At his death, Dantzig was the Professor Emeritus of Transportation Sciences and Professor of Operations Research and of Computer Science at Stanford University. In the mathematical theory of optimization, duality is the principle that states that optimization problems can be seen from two perspectives, the primal problem or the dual problem. If the primary is a minimization problem, then the dual is a maximization problem, and vice versa. Any feasible solution to the minimization primal problem is at least as great as any feasible solution to the maximization dual problem. Therefore, the primal solution is an upper limit of the dual solution, and the dual solution is a lower limit of the primary solution. This fact is called weak duality. The duality gap is the difference between the primal solution and the dual solution. If D is the optimal dual value and P is the optimal primal value, then the duality gap is equal to P, D. In minimization, this value is always greater than or equal to 0. If the duality gap is 0, the duality is strong, otherwise, the gap is strictly positive and the duality weak. Duality is a powerful and widely used tool in applied mathematics for several reasons. The dual problem is always convex, even if the primal is not. The number of variables in the dual is equal to the number of constraints in the primal. The maximum value reached by the dual problem is often equal to the minimum of the primal. An optimization problem must be analyzed from 2 points of view: feasibility, when the feasible zone of the primal problem is satisfied, and optimality, when the feasible zone of the dual problem is satisfied. In general terms, in computational optimization it can be considered that there are two types of basic algorithms, the primal and the dual, and a third class, the primal dual, which is a mixture of the previous two. The primal movement is carried out in the feasible primal zone, seeking to achieve optimality in the feasible dual zone. The dual movement is carried out in the feasible dual zone, seeking to achieve feasibility in the feasible primal zone. In a primal algorithm, another duality gap is often reported, which is the difference between any infeasible dual solution and the value of a feasible but suboptimal iteration for the primal problem. When the gap between the primal and dual zones is closed, convergence has been achieved. This gap quantifies the discrepancy between the true value of the primal problem, in a feasible but suboptimal iteration, with the best possible dual solution, unfeasible but complying with the principles of optimality. The value of the dual problem is equal to the value of the convex relaxation of the primal problem. The analysis for a dual algorithm is similar. Karush-Kuhn-Tucker conditions, KKT, a set of fundamental equations and mathematical optimization to find optimal solutions in problems with constraints, generalizing the method of Lagrange multipliers and applicable to nonlinear programming. Was created by William Karusha, professor at California State University at Northridge. He was a mathematician best known for his contribution to KKT conditions. Harold William Kuhn, an American mathematician who studied game theory. He won the 1980 John von Neumann Theory Prize with David Gale and Albert Tucker, and Albert Tucker was born in Oshawa, Ontario, Canada, and earned his M.A. at the University of Toronto and his Ph.D. at Princeton University. KKTs are first-order conditions necessary for a nonlinear programming solution to be optimal, provided that some regularity conditions are met, allowing inequality constraints. KKT generalizes the Lagrange multiplier method, which is limited to equality constraints. KKT did not solve the problem directly, except in the few special cases in which a solution can be derived analytically in a closed form. In general, many optimization algorithms can be interpreted as methods to numerically solve the KKT system of equations. When primal restrictions are met, the penalty in the Lagrangian is nullified and loses meaning. When primal restrictions are met, the penalty in the Lagrangian is nullified and loses meaning. In the case of linear models, the Lagrangian gradient with respect to the dual variables is independent of the Lagrangian gradient with respect to the primal variables. This independence of feasibility zones, dual and primal, is important in the case of algorithms for solving linear problems, as they can be worked on independently. The principle of duality is summarized as feasible dual solution less than or equal to the feasible primal solution. The duality gap is equal to the absolute value of the difference between the dual solution and the primal solution, and it is equal to the absolute value difference between the Lagrangian and the objective primal function. Studies on the equilibrium of markets go back many years. Robert Dorfman, Paul Samuelson, and Robert Solow are best known as the co-authors of the landmark 1958 book, Linear Programming and Economic Analysis, commissioned by the Rand Corporation. This text was the first comprehensive treatment to bridge the gap between standard economic theory and the post-war developments in linear programming. It is considered a classic in mathematical economics for integrating traditional theory. It connected linear programming to classic theories of the firm and general equilibrium. Game theory. It explored interrelations between von Neumann's theory of games and linear programming. Input-output analysis. The book provided a rigorous mathematical foundation for Leontief's input-output models. Samuelson and Solow were awarded the Nobel Prize in Economics. Economic Theory of Markets, Antoine-Augustin Cournot. One of the best-known works is the one published by Cournot in 1838 in his book Recherches sur les principes mathématiques de la théorie des richesses, in which he constructs a theory of oligopolistic agents that includes monopoly and perfect competition as extreme limits. Oligopolistic Economic Equilibrium, Heinrich Freiherr von Stackelberg. The work published by Stackelberg in 1934, in which he studies the equilibrium conditions of monopolies and oligopolies with dominant agents, as is the case of the electricity sector, is very important. The economists learned to think systematically about the adoption of rational measures in decision-making processes, and it became natural to think about the application of that rationality to social problems other than the production and distribution of products. But applying this rationality in more general areas, without the traditional structures of a market, also required a more general approach. The search for such a structure was undertaken in 1928 by John von Neumann with the development of the basic principles of the so-called game theory, which was concretized with the publication, together with Oscar Morgenstern, of the book Game Theory and Economic Behavior in 1944. During this period, it is worth mentioning Wald's work published in 1935 and 1936, which provides, for the first time, evidence of different qualitative characteristics of equilibrium. Competitive Economic Equilibrium, John Nash. In the 50s, the new era of equilibrium studies began with Nobel laureate John Nash's first work on the theory of non-cooperative equilibrium, which can be considered one of the most important intellectual advances of the last century, due to its great impact on the economic sciences and, in general, on the social sciences. To understand the importance of Nash's work, we must begin with the definition of economics itself. A generation before Nash, economics was defined as a social science specializing in the study of the production and distribution of goods and services. By this definition, Nash's work could be considered mathematical research beyond the boundaries of economics. Today, economists define their field of action more broadly, as a science related to the analysis of the incentives that move all social institutions. Nash's contribution played a central role in redefining the scope of the economy. Carnot's work can be considered a precursor to Nash's work, and for this reason the Nash-Carnot equilibrium is often discussed, but the reality is that Carnot did not attempt to articulate any theory about equilibrium. Nash's theory, based on the maximization of the utility functions of each agent, is simply the mathematical formalization of the ideas that Machiavelli had qualitatively proposed, in 1513 through his famous book The Prince, about non-cooperative games. One of the fundamental relationships between optimization and economics corresponds to the concept of market equilibrium, which is achieved from the understanding that in a rational market all agents will try to optimize the achievement of an objective, usually maximizing its benefits, which each agent achieves through an optimization model. The joint solution of market equilibrium is achieved when all agents obtain positions in which they optimize their objective, considering that the other agents do the same. This comprehensive model can be called the market equilibrium model. To understand the mathematical behavior of equilibrium models, it is necessary to start from the understanding of optimization models, since from a rational point of view, not necessarily economic, any agent acting in a system will try to do it in the best way according to the principles that determine the objective of its existence, which means optimizing their behavior according to their performance measure. The solution to the equilibrium problem will be found at the points where the mathematical conditions that determine the optimization of the performance measure of each of the agents are met, considering the effects that the decisions of each agent have on the other agents. Based on the above, the study of the mathematical conditions of equilibrium models begins by studying the mathematical conditions of optimization problems, and from there it extends to other mathematical problems that are also appropriate for studying and solving the equilibrium problem of systems of any kind. The following types, formats, of problems should be considered. Nonlinear programming problem. Nonlinear complementarity problem. Variational inequality problem. Mathematical problems with equilibrium constraints, and fixed point problem. It is important to note that none of the alternatives is the best, and that they are complementary and, in some cases, appropriate or difficult to implement. The image is present in a simple way the equilibrium of a market. If the market is perfect, the equilibrium point is where the social surplus is maximized, which is equal to the sum of the consumer surplus plus the producer surplus. In traditional and old models of electricity markets, an inelastic, price-insensitive demand curve is assumed, as shown in the diagram. This implies a consumer with an infinite willingness to pay for electricity. With respect to the objective functions of the models, the dual maximizes the value of resources, and the primal minimizes the cost of production. The image shows the algebraic formulation of the primal and dual models. A real demand curve, associated with a model with multiple plants and generation resources, which has multiple equations, for a linear model will look like a step curve, where each step is related to the activation of a constraint. Supply curves are adjusted to the cost structure of generation plants. The image shows a demand curve for a real system, which has hydraulic and thermal plants. At the base are hydropower plants. Since there is no market for water resources, they are all similar and, when the transmission system is ignored, they have a degenerate solution. The staggered part of the curve corresponds to the activation of each thermal plant, due to the cost of the fuel located in the plant. If hydroelectric generators can control their part of the supply curve, reducing the quantity offered, they will be able to increase the price of electricity. This can be a typical case of dominant power in the market. A modern mathematical model can do all the math, to dynamically determine the strategic price. Electricity markets optimization. Case: degenerate solutions. A wholesale electricity market, WEM, is based on a locational marginal price, LMP, system in which an independent system operator, ISO, collects bids from generators and consumers to solve the problem of market settlement. The essence of economic dispatch is to select the mix of generation resources that is least costly, or that maximizes social surplus, to meet the demand for electricity subject to available resources. This process ensures that the transmission network is used as efficiently as possible, an activity that cannot be achieved without the coordination of an ISO, because electricity flows according to physical laws, such as Kirchhoff's, which makes it impractical to enforce physical property rights over transmission capacity in an interconnected network. Let's analyze the degenerate solutions for the case of linear programming, PL. To do this, we will identify the primal problem as P and the associated dual as D. A mathematical programming solution is degenerate when there are primal variables in the basic solution that are equal to 0, which causes the solution to involve multiple optimal solutions, which are equivalent because their reduced cost is the same for all of them. On the other hand, the dual variables of the constraints involved will be equal to 0. Dual solutions of degenerated problems. Dual variable is equal to the gradient of the objective function by changes in the resource vector associated with the constraint. Degenerated dual variable. Due to resource substitution, a change in the resource vector of a variable that is part of the degenerate solution, the dual variables of constraints that include this degenerate variable are equal to 0. Since the variation of the degenerate variable can be replaced by another associated degenerate variable. Let's consider a linear optimization problem, whose feasibility zone is a closed polyhedron, with n extreme points, in this case 6. The contour lines of the objective function will instruct an algorithm to move out of the viability zone to optimize a convex problem. If the problem is not degenerate, the optimal solution will correspond to one of the extreme points of the polyhedron. If the resource vector is infinitesimally perturbed for any active constraint, it will automatically change the value of the solution by an amount defined by the dual variable of the constraint that has been perturbed. For non-active constraints, the corresponding dual variable will be equal to 0. If the isolines of the objective function are parallel to a hyperplane of the constraint polyhedron, in this case a line, there will be at least as many optimal ends as the extreme points of the polyhedron hyperplane. In general, all the points that are part of the convex set, defined by the hyperplane of the constraint polyhedron, will be a solution. If the resource vector is perturbed infinitesimally, in any active constraint other than the line with the objective function, the value of the solution will not change. This implies that there will be dual variables of active constraints, equal to 0. Hence the strict complementarity of the theory of duality, which says the variable slack multiplied by the dual variable will be equal to 0, and one of them will be different from 0, it will not be fulfilled. Another case of degeneracy occurs when the duality gap is not closed, such as when the solution produced by the algorithm does not reach the optimum, usually for convergence reasons. This usually occurs in discrete optimization problems, where closing the duality gap may be infinite. Degenerate solutions are found in convex set of equivalent suboptimal solutions. Another aspect that can influence the degeneration of a problem is related to the algorithms used to solve it. There are two alternatives. First, the outer point algorithms, such as simplex-type algorithms, which traverse the viability zone along the edge looking for optimality. In this case, the algorithm will tend to stop at the first extreme point that meets the optimal conditions, and for which it can be shown that there is no better solution. If the solution is degenerate, the algorithm may not be able to prove that it is in a solution to the problem and will follow the endpoint enumeration process until the last endpoint, when it will be able to prove that there is no better solution. This solution is basic, feasible and optimal. At the interior points, or penalty and barrier algorithms, the algorithm traverses the internal viability zone, quickly looking for the boundary where the solution is located, which will possibly be close to an extreme point, but often does not correspond to a feasible basic solution at an extreme point. If necessary, a crossover process should be performed to obtain a basic feasible solution at an extreme point. This will be the feasible basic optimal solution to the optimization problem reported by the algorithm. Feasible basic solutions are necessary to continue the optimization processes based on a dual simplex algorithm. In a strictly complementary optimal solution, for each primal variable greater than or equal to 0, the corresponding dual clearance is strictly positive. Each non-degenerate model has a strictly complementary optimal solution. This implies that if the slack variable is equal to 0, the corresponding dual variable must be strictly positive. The following key points should be considered with respect to the solutions of the primal problem P, and the dual problem, D. If a basic solution I, xp, is equal to 0 for some basic variable, then we have a degenerate primal optimal solution. It is quite possible that we will then have multiple optimal dual solutions, but this is not necessarily the case. If D has multiple optimal solutions, then each optimal basic solution for P is degenerate. A dual feasible solution is degenerate if more than m dual constraints are exactly maintained, equivalently, if less than n-m dual constraints are strictly maintained. If D has a non-degenerate optimal solution, then P has a unique optimal solution. If P has multiple optimal solutions, then each optimal basic solution for D is degenerate. If P has multiple optimal solutions, then each optimal basic solution for D is degenerate. Degeneracy and optimization of industrial systems. The origins of degeneration may be several. For example, considering that the dual variables, equal to the Lagrange multipliers if the strict duality is satisfied, are equal to the gradient of the objective function with respect to the resources associated with the constraint. To establish the value of water at the beginning of a period, the price of the water resource, in dollars per million cubic meters, must be equal to the maximum of the dual variables of the continuity restrictions in the reservoir. This value should be equal to 0 if there is abundance in the reservoirs, or equal to a positive value if the water resource is being depleted. If the water stored in the reservoirs is not enough to cover the demand for electricity, it leaves the system dependent on water inputs and thermal generation capacity. Several important mathematical and computational problems arise from degeneracy. Greater difficulty in solving optimization problems, therefore greater computational effort. In certain algorithms, degeneracy can produce cycles, since cycles of degenerate solutions could be selected in which the displacement condition in the gradient of the function must comply with being positive and not simply being greater than or equal to 0. Difficulty comparing solutions obtained with different algorithms/models. With the same algorithm under different parameterization, and minor changes in model parameters. Degenerate solutions can apparently produce large visual changes, different operating profiles, while maintaining in all cases the same value of the objective function. Other important problems are indefiniteness of the dual variables which are equal to 0 for the constraints involved in degeneracy. An important problem when dual variables are to be used as part of a process to determine prices of an agent in a market. Degeneracy in a discrete problem can lead to not being able to prove the optimality, or the feasibility, of the solution, since it involves a combinatorial enumeration of multiple discrete variables that can be non-enumerable. It is more common for degeneracy to be a problem associated with the input data, rather than with the formulation of the mathematical problem. A well-formulated problem can be degenerated by the instance of the problem. Degeneracy occurs in all kinds of optimization problems. Continuous and discrete, and linear and nonlinear. Common cases that produce degenerate solutions. Oversupply of resources whose direct cost is 0, examples, water resources, electrical power losses. Resources whose costs are equal. Imperfect mathematical formulations. The video. Mathematical optimization models. Degenerate solutions. Take a closer look at this case. Electricity markets optimization. Case, duality gap. In mathematical optimization, the duality gap is the difference between the value of the objective function of a primal problem, and the value of its corresponding dual problem. The marginal cost problem, when there are discrete variables in the context of short-term auctions, such as energy, refers to the short-term competitive equilibrium, agents should have no reason to change the allocation assigned by the auctioneer, which means that agents should recover operational costs in the auction. However, this is not always enough to choose between traditional pricing schemes, so it is necessary to look for alternative or complementary schemes. In auction pricing with complex rules using optimization models, when the problem is convex there is no duality gap, such as linear programming, but this does not occur in the presence of non-convexities. More precisely, in areas where the problem is not convex, small changes in the price signal cause large leaps in the solution of the dual problem, making it impossible to satisfy the loose equation, the supply-demand equilibrium. As a result, the solution of the primal problem satisfies exactly all the constraints but differs easily from the solution of the dual problem. This is the case with mixed linear programming models, which are not convex. The figure shows the classical geometric illustration of Lagrangian dualization, which contains optimal primal value, optimal dual value, duality gap, and best supporting hyperplane. The points in the set, indicated by the gray area, denote an optimal value. This case is of a zero duality gap. The points in the gray set indicated that the case corresponds to a positive duality gap. The figure illustrates the dissection of fx and θ mu in a non-optimal feasible primal solution, epsilon, and a non-optimal dual solution, delta. The epsilon and delta functions are introduced, and the figure shows their optimal values. Since mu is not optimal, the line θ equal to z plus mu multiplied by ni supports the set of non-optimal solutions, color white, at only one point x, which may be feasible or infeasible. The case corresponds to a duality gap. Understanding the duality gap. Dual variables do not recover all costs, the unrecovered cost is equal to the magnitude of the duality gap. This will imply losses for market agents. The use of optimization models in a market environment continues to face several challenges. This section discusses the duality gap problem in simple auction optimization models. The publications of Madrigal and Quintana have been taken as a reference. Madrigal presents an example of a plant dispatch that contains the data of 5 bidders with linear and constant startup costs. Although the model is simple, the results help to understand the conditions under which optimization models can be used and the information they provide to conduct electricity auctions. The operating cost of a plant is made up of an initial startup cost plus a linear operating cost. The model includes a binary variable equal to 1 if the plant is in operation and 0 otherwise. The operating power of the plant is a continuous variable. The MPA optimization problem for solving auctions is called MPA. The introduction of binary variables makes MPA a non-convex optimization problem, and therefore the duality gap may exist in some situations. This type of bid format, while simple, is designed to determine a market price for energy, and all participants will receive that price for the energy they sell to the market. In theory, the price should be such that it recovers the costs of the participants. To learn auction behavior, the cost minimization auction is solved for the following demand levels: 52, 110, 130, 190 and 210 megawatts. Madrigal analyzes the case of 5 bidders with the following parameters. Alpha equals startup cost, beta equals to operational cost, and maximum power. The cost minimization auction is solved for the following demand levels: 52, 110, 130, 190 and 210 megawatts. The complete list of dispatch possibilities can confirm that the solutions presented are optimal in all demand cases. The table below summarizes the costs, revenues, and profits for each of the solutions when the price is equal to the smallest optimal dual variable, when there is a balance. In equilibrium, this rule leads to positive profits for all bidders and is analogous to a first price auction in which the last bidder makes a profit equal to 0. In imbalance, some of the bidders do not recover the cost, and the total unrecovered cost is equal to the duality gap. Corner indicates the duality gap in the instances analyzed. Pi corresponds to the dual variable for each case of demand and each bidder. The total supply function is shown in the figure, for the 5 demand scenarios. Qualitatively, the table presents the results for the 5 demand scenarios. The solution is analyzed mathematically. 52. There are infinite optimal solutions. Since 30 megawatts can be supplied in an infinite number of ways by suppliers 4 and 5, assigning a power equal to x to supplier 4 and 30 minus x to 5, for values between 10 and 20, the same objective function value, $2,140, is produced. There is no market equilibrium, and the optimal dual variable is unique. 110. There are two optimal solutions. There is no market equilibrium, and the optimal dual variable is unique. 130. There are multiple optimal solutions, only two of them are shown. The first solution contains offers 4 and 5, and the second contains offer 3. There is no market equilibrium, and the optimal dual variable is unique. 190. The primal solution is unique, but there are several equilibrium prices in the range between 25.78 and 26.75. 210. There is a single equilibrium price and two optimal primal solutions. The costs, revenues and benefits of each of the solutions, when the price is equal to the smallest optimal dual variable, and there is an equilibrium in the market, this pricing generates positive benefits for all bidders. This rule is analogous to a first price auction in the sense that when equilibrium exists, the last bidder, marginal bidder, makes a profit equal to zero. For cases in disequilibrium, some of the bidders do not recover the cost. In all these cases the total cost not recovered is equal to the magnitude of the duality gap. Qualitatively, the table presents the results of the 5 demand scenarios, for bidders. It is analyzed what they think after the auction. 52. At a price of $15.80/MWh, bidder 2 wants to increase its production to 50 megawatts to maximize its profits. 110. Since price is between 25.78 and 26.75, bidders 4 and 5 want to reduce their production and operate at zero profit. 130. All the possible optimal solutions to supply 30 megawatts between tenders 4 and 5 generate the same unrecovered cost of $46,667. At the price of $25.78/MW, bidders 4 and 5 wish to reduce their production to zero to avoid negative profits. In the second case, bidder 3 would like to increase to maximum production to maximize profits. 190. There is equilibrium with an optimal program. The bidders agree with the allocation made. 210. There is an equilibrium between two optimal programs, both solutions offer the same benefit. Although bidders 4 and 5 are not scheduled, they don't care about the deadline that is finally implemented. The 110 and 130 megawatt scenarios show that some bidders want to withdraw from the auction, but others want to increase their bid. In the other scenarios, the situation is more attractive. There are bidders who want to offer more or who do not care what happens. The duality gap complicates the mathematical analysis of auctions when they are not convex. All science as it grows toward perfection becomes mathematical in its ideas. Alfred Whitehead. Thank you very much for your attention.